Hello and welcome everyone. Today we shall be looking at problem number 2.4.3 in your book. It's called hospital staffing. And in this problem, we have a hospital that receives packages. And these packages are processed by the employees who are employed within the hospital. So for the next year, this hospital is expecting to receive a total number of 127,139 packages. And it knows the distribution to be exponent or rather Poisson arrival process, and for the employees to process a certain package, the parameters are also known. So to process a package, it follows a triangular distribution, and the most likely value is 10 minutes, and the minimum is 7 minutes, and the maximum is 15 minutes. So the also the hospital is open for a period of 255 days for within that year, and essentially the number of packages that they are going to receive on an average would be 127,139 divided by 255, which comes out to be approximately 498.6 packages on a daily basis. So if this is the number of packages that they receive on an average daily, so the inter-arrival time between two packages, that comes out to be 24 upon 498.6 hours. So this is again a Poisson arrival process. And for the employees who kind of process the packages, they also have a working schedule. So they work from Monday to Friday during the week. They start working at 8 a.m. in the morning, and they leave the facility at 4:30 p.m. However, during this period of, I guess, like 8.5 hours, they take a 30-minute lunch time and a 15-minute breaks twice daily, which I would let's call it like a tea break. So they have two tea breaks and one lunch break. So the tea breaks are 15 minutes and the lunch break is 30 minutes. So essentially, effectively, they work for 7.5 hours every day, and the management wants to know how many employees that they need to hire for the next year who would be able to process all the packages that they receive, which is like 127,139, a total number of 127,139 packages. So by doing some calculations based on the averages and all, the management finds that they would require a total of 11.1 employees. And so in our model, we are going to start with 11, I guess, like 11 employees, and then we'll see that whether they would be able to process all the packages or not for the given year. And if not, then we'll start increasing the capacity by 1 to 12 or 13, and wherever we find like they are able to process all the packages. So I have already modeled this. So in the create module, which I'm calling packages arrive, I have defined it to be an exponential distribution with the time between arrival to be 24 upon 498.6 hours. My entities per arrival is 1. And remember, the maximum arrival for the year would be 127,139. So this is what I have specified over here instead of infinite. And first creation, I'll keep it as zero point 0.0. For the process module, again, it's a cease delay release. We have employees who kind of processes the module, or rather the packages that come into the hospital, and it's a triangular distribution, and the processing times are 7, 10, and 15 minutes, where 10 is the most likely or mode value, and 7 and 15 are the minimum and maximum values respectively. um, I don't think I have anything else here. So we go to resource. And again, like after a package is processed, it gets disposed out of the system. So if we go to resource, like I said, I'll start with a capacity of 11 employees for the year. However, there is a small change over here which is kind of reflected in the failures. So remember, we talked about the schedule that they have for every day. So they work from 8 in the morning to, I guess, like 4:30 in the afternoon, was it? Yeah, 8 in the morning to 4:30 in the afternoon, and within that time period of 8.5 hours, they also take two um, tea breaks, which lasts for 15 minutes, and one lunch break, which lasts for 30 minutes. So those breaks are kind of defined within failures. So it's like they have a certain uptime is the time for which they work, and then the downtime represents the time for which they'll take a break. So after they return from the break, they will have another uptime until they break again. So what I'm assuming in this model is that, like, we'll have one tea break in the morning, then we'll have one lunch break at noon, and then we'll have another tea break in the afternoon, I guess, and they'll work and leave at 4:30. So that's why we have defined four different failures, which I'm calling as failure one, two, three, four. And then we have the failure rules implemented over here. I'll talk about the failure rules later on. Let's go back to the failures that I have. So we are calling them failure one, two, three, four. And where have I defined them? So if you go to advanced processes and click on the failure spreadsheet, here you'll find the names that I have specified. So failure one represents the time when they start working. So they start at 8 a.m. in the morning, and I'm assuming they work for 2 hours. And after 2 hours, which is like from 8 to 10, they work, and they'll take a downtime of 0.25 hours, which represents a 15-minute tea break. So they'll have this downtime, and after this is done, they'll come back again from 10:15. They'll work until 12 noon, which is 1 hour 45 minutes. They'll have another uptime, and starting from noon they will take a lunch break of half an hour, which is 30 minutes, and that's a downtime. So after they take that lunch break, they come back again to work starting from 12:30. They is work for, I guess, until 2:30. That's what I'm assuming. And then starting from 2:30, they'll take another 15-minute tea break, which would be another downtime and represented in failure 3. And after they take that tea break, they'll come back again at 2:45 and start working again, and they'll work for another 1 hour 45 minutes until 4:30 in the afternoon. They'll work, and then they'll break again for the day, and this is like 15 and a half hours, which represents they break off at 4:30, they go back home, they take rest, do whatever, and then they come back the next morning at 8 a.m. So the time between 4:30 p.m. the previous day and 8 a.m. in the morning for the next day would be like 15 and a half hours. So that's my downtime for that particular day, I would say, when they leave the facility. So this is all defined. Now, coming back, we talked about the failure rules that I have, right? So if you want to see, like, what, you know, um, how would you enter, like, the values in each module, what each module represents, and stuff like that. Here you can click on that help, I guess, like icon over here, and then click on the module that you want to kind of explore and see what each of the I guess, like things mean over there, and how to input stuff to represent a scenario that you're working towards. So if you click on the resource module and go to remarks over here, you'll see the three types of failure rules that we have, and it's presented in bold letters. So the first one is ignore, the second one is wait, the third one is preempt. So let's talk about each one of these. So think about a system where, like a doctor or an employee is supposed to work for 2 hours. So starting at 8 in the morning till 10 in the morning, so 8 to 10, and then he's supposed to take a break of, like 20 minutes, for example, and then he'll come back again and work, I guess. Um, so when he's supposed to take a break at 10, suppose there is an patient that he's attending to, or if it is, some kind of surgery, there is a patient who is still undergoing a surgery at that point of time. What does he do? Does he leave the patient and be like, hey, my break time starts right now, I'll keep you waiting in my office, or keep you waiting in the operating room, and I'll take my break and I'll come back again? Does he do that, or does he, like, serve that patient, and then he changes his status to taking a break, and then he takes a break and comes back again. So these are the type of rules which kind of determine what the action of the doctor, or it can be applied in, I guess, like manufacturing problems as well, what the action of a machine would be. So the first rule is ignore. So it starts at time duration, the schedule changes or failure immediately, but allows the busy resource to finish processing the current entity before affecting the capacity change. What it means is like, suppose he was supposed to take a break at 10 until 10:20, but he had to like attend another extra 5 minutes for the patient. So he becomes free to take his break at 10:05 instead of the previously scheduled downtimes, which would have started at 10. So in that case, in the case of ignore, what he's going to do is he'll start his break at 10:05, just after he has attended the last patient. However, the time when he comes back again to work, that would remain the same, which means if he was previously scheduled to take a break starting at 10 until 10:20 and then resume his job from 10:20 onwards, so since he got a little delayed because of like he had to attend the last patient, so he actually starts taking the break at 10:05. However, he comes back to work at 10:20 again. So the time at which he kind of returns back to work doesn't change. So what changes is the time when he starts to take the break, and also the break duration. So instead of like having a 20-minute downtime or 20-minute break, he's going to have an effective downtime of 15 minutes right now. So that is ignore. So what is wait? Wait is when he kind of postpones or delays his break, but he'll be taking the break that he's scheduled to take. So that is, if we're supposed to take a 20-minute break, he will take a 20-minute break. So suppose he was supposed to start his break at 10 and then go until like 10:20, after which he would have to come back to work. So because there was one patient in the clinic he had to attend to, he got delayed by 5 minutes. So essentially, his break would start now at 10:05. However, he'll take extend his time to kind of come back to the system by 5 minutes because he got delayed by 5 minutes in the first place. So he actually like kind of shifts his break time that he or downtime that he's going to take. So that is wait. So what changes in the wait is like the time at which he starts to take his break, as well as the time at which he kind of returns back to the system, his next uptime. What doesn't change is the time for which he'll be taking the break. So it still remains 20 minutes. So he was scheduled to start at 10:20. Now, since he got delayed by 5 minutes, he'll start back work at 10:25, essentially. The preempt rule is a little different from ignore and wait. It means like when he's supposed to take a break, he'll take the break, no matter how many patients, whether he has a patient waiting or not, which can spell disaster in the case of I guess, healthcare operations, because if you're a doctor and you're supposed to take a break at 10 o'clock, you cannot just keep your patient waiting and say, I'm supposed to take a break right now, I'll come back and attend to you later. Or you cannot just leave a surgery in between. You cannot just leave in between a surgery and say, yeah, this is my break time and I'll take it and I'll come back and I'll kind of stitch you up or whatever. So that doesn't happen. But this preempt can happen in other scenarios. For example, in manufacturing processes, if you have a machine running, and suppose I have a drilling machine and it has got a drill bit, and suppose this drill bit was supposed to break down at 10 o'clock, it will break down at 10 o'clock, no matter whether there is a part that is being processed at this point of time or whether it's in idle mode or not. So it will break down at 10, and again there would be a downtime to kind of fix the machine and put a new drill bit over there, and it will start back on. So in preempt, what happens is like whether there is a like entity that is being processed at this point of time or not, the resource status changes from being busy to idle at whatever time it was supposed to start, I guess, the break at or the downtime at. So again, like if it was idle, well and fine. If it was not, then it will take that break from 10 to 10:20 anyway. So that is preempt. And preempt, again, like I said, it's not a very common stuff that you'd see in hospital settings, but it's more common in I guess, in manufacturing processes where we have machines or I guess like failures and stuff like that. So now coming back to my resources, okay. So I do have the failures defined over here. So failure one is wait, right? So wait means he is going to take his 15-minute break no matter what. So if he started at 8 in the morning and he went until like 10 uh, f- when he starts to take his tea break and all that, if it went a little more than 10, say at 10 or 2, he will take his 15-minute break starting at 10 or 2. So that's why we have wait, and the same goes for the lunch break and the afternoon tea break as well. He will start, he'll just delay his I guess like time to take those breaks and all that. However, he will take two 15-minute break for the tea breaks, and he'll take one 30-minute break for to have his lunch and all that. For failure 4, which represents the time at which he leaves the system after his day's work and all that, that is ignore. Why? Because he's supposed to leave the facility at 4:30 and come back again at 8 in the morning the next day. However, because there were one, I guess, like entity or package that he was still like processing at 4:30 p.m. In that case, and it took him like 5 more minutes, so he essentially finished his like processing work at 4:35. Irrespective of when he finishes or whether he gets free at 4:30 or not, he's supposed to report back to the facility again at 8 in the morning. So that's why we have ignore. So in this case, the break that he'll be taking, say, which was supposed to be starting from 4:30 in the afternoon till like 8 in the morning, that would get reduced because there were I guess packages that he was attending to at the end of the day. So that's why I have an ignore for failure 4, and I should be good to run right now, right? And here, my setup, I have defined it to be 255 days, and hours per day is 24, and base time units I've kept hours, and everything I've kept, I guess, yeah, I'm having like one replication, so the others, the other things I haven't changed at all. So here I can run this model and let's see what happens here. You can fast forward and you see I get an error which tells us that there has been the maximum capacity has been exceeded at time 9.42 hours. So what does 9.42 hours mean? 9.426 hours. So this represents a time at the end of the first day. So it's like, first day's work has been completed, and so at around, I guess, like 8:30 hours. And after that, uh, it starts, like receiving the packages for another 1 hour. And at that point of time, it kind of, the number of packages that are within the system kind of, exceeds 150. So that is where we get this problem. So we have to circumvent this. If you have a full version, this is a student version, like I said, which kind of restricts this problem. If you have a full version, you'd be able to run this and see what happens. However, if you have a restricted version, this is not going to help you because you need to see you won't be able to see like what happens and all that. So if I increase the capacity to like 12, let's see whether anything changes or not. Again, it kind of stops around the same ish time, I'll say 9.4 to 6 hours. That's when your um the number of packages that kind of exceeds like more than 150 and all that. Again, if I increase it to 13, still we get that problem, right? So we wouldn't be able to see our reports or know whether 11 or 12 or 13 employees are sufficient to kind of process the total whatever number of packages that they were going to receive for the year. um, but again, like if you have the full version, it's always a possibility. However, one of the ways by which I tried to circumvent this problem was by saying that the packages only arrive during those times for which the employees work. So again, what I did was like, I put up a schedule over here, and this schedule kind of follows the times for which the employees are working. So during a failure, which is where they are taking a break, a lunch break or tea break, or they have gone home and all that, I'm not receiving packages. It's only when they are within the system and working, that's when I am letting the packages come in and all that. However, that also ran into a problem of like running beyond 150 entities in work in progress, and that happened when they took the lunch break. So it was around 4 point something hours on the very first day. So I couldn't run that in the student version as well. So we have to keep in mind that this is something that this problem wouldn't allow us. So the another way by which I kind of circumvented this problem was, let's talk about that, is having a modified hospital staff in problem. What I'm trying to do over here is say that like all the 7 point, so essentially like the employees would work for like infinite amount of time, like there wouldn't be any breaks, but it would be like I'm clubbing together all the 7.5 hours of work for the whole year uh, into like one single, I guess, stream of 7.5-hour work. So essentially there wouldn't be any breaks over here. The triangular distribution remains the same here in the resources. What I'm saying is that there is no failure. So essentially effective, they would be following their effective number of work hours that they have for the whole day and all that. And that's like, they're working for a continuous of 7.5 hours and all. And here I have a capacity of 11 to begin with. And the packages arrive, this would be like 7.5 divided by 498.6 hours. Why? Because again, like for the resources for the employees that I have, we are effectively just looking at the time for which they would be working, and during this time, that is for the 7.5 hours, there would be like 498.6 packages on an average that the facility or the hospital would receive. So essentially, it's like I'm just looking at the those periods of time for which the hospital would be busy, for which there would be work going on in the hospital, and I'm just removing out all the breaks and all the, I guess, like time for which the resources wouldn't be available out of the system. So again, I'll have like a maximum arrival of 127, 139 entities or packages, and I'll start, like I said, my resource with 11 employees, and let's see what happens. So here again, I'm looking at the average number in queue, and I want to see whether it reaches a steady state or not. So here at 14.93 hours, which is around 15 hours, it kind of exceeded the 150 entity limitation. And we see until that point of time, the average number in queue kind of kept on increasing. So this is again, if you look at the schedule utilization, you'll find that, this is more than one. And since it is more than one, like we'll have a non-steady state system, and that's why we do not reach any steady state value over here. It keeps on increasing until a point of time when, like the number of entities within the system kind of, exceeds the 150 limit mark and all. So 11 employees wouldn't be able to process the total number of packages that we have. So here I'm putting in 12 employees, and let's see what happens here. So it's still running, which is good. Okay, so again, it exceeds this 150 entity limit mark at around 900 hours. However, if you look at the average number in the queue, this is kind of, like flattened a little bit. By saying like it has flattened, I mean like, it isn't as steep as it was in the case of the 11 employee uh, scenario that we had in the previous case. However, we still have the problem that it doesn't reach a steady state. It still keeps on increasing. So we'd probably need more than 12 employees to kind of process the whole, how many packages were there? 127139 total packages and all. So here I'll increase the capacity to 13 right now. And let's see this scenario, whether in this scenario we are able to run or not. Okay, so it has run more than 1,000 hours. So yeah, so we were able to run the whole model using 13 employees. And let's look at the queue parameters first then. We had a wait time of 0.04 hours in the queue, average wait time, and then a package spent average time of 0.2242 hours in the system. And my number waiting on an average was 2.46 packages at any given point of time on an average. And here, if you look into the graph that we kind of plot that we have generated here, the average number in queue Yeah, it was 2 point something that we just saw. And this is able to reach a steady state when we are using 13 employees. So our recommendation to the management would be to have 13 employees kind of stationed at the, I guess, the hospital to kind of process the total of 127139 packages and all. So again, I have kind of, I guess, recorded the plots that we generated for 11, 12, and 13, and 14 employees as well. So here, like and the 14 employee, obviously, like once it is 13 or more than 13, we would be able to achieve that steady state value. And what happens when we employ 14 employees over in the hospital is like the average number in queue that kind of decreases. So it was 2 point something here for the 13 employee problem, but 13 employee scenario. And for the 14 employee scenario, it kind of got to less than one. And we'd expect that to happen. Why? Because like more employees, the faster they're able to process, so less amount of waiting in the queue, and then also like less number of packages that are waiting in the queue. So again, what we do need to see is like if we want to kind of um, if our, I guess, like if the hospital management doesn't have the necessary tools to kind of hire 13 employees and all, there are a lot of ways in which they can like do it with, I guess, like 11 or 12 employees. One of them can be by extending the number of days or number of hours of work per day for the 12 or 11 employee scenario. Or it can also be like the employees can be trained to kind of reduce their service times. And in those cases we'd be able to achieve, I guess, like steady state when we have 11 or 12 employees. But maybe there may be additional costs associated with having to, I guess, make the employees work for extra hours, or like to kind of train them to kind of improve their processing times for the packages and all. So we need to keep those things in mind, whether like how much time we can spend for, I guess, like how much time we can allow for package to wait in the queue, or how many packages we can have on an average, or what would be the allowance of the number of packages that we can have in waiting in the queue and stuff. And also we need to keep in mind whether we want to hire more number of employees, or whether we want to increase the number of working hours, or whether we want to train the employees, because these all have associated costs with them and all that. So here we just saw that um, that in this case, that if the management needs to determine the number of staff needed to be hired to process a team of 13 employees, yeah, we talked about that. And also result in a batch of unprocessed packages, yeah. So any less capacity will result in a batch of unprocessed packages and stuff. We also talked about the capacity can be reduced if employees are trained to process the packages faster, or by increasing the effective number of work hours per day. We talked about that. We also need to keep in mind over here that if the packages that are coming in is time sensitive. For example, like if the packages that come in needs to be put in the refrigerator as soon as possible. Like, they cannot wait for, I guess, more than 2 hours in the system and all that. So there may be some packages that are time sensitive, and there may be other packages which are not. So again, those are some of the scenarios that, like, the management needs to keep in mind, and only doing a discrete event simulation would help them to kind of understand how the system behaves, how many people they would be requiring to hire for the next year, and what would be the waiting time, average waiting time for different types of packages that they are receiving, or what would be like or how many packages would be waiting, like on an average in the queue and all that. So, and that would help them make a better cognizant decision in the end. So thank you for joining in. We will see you next time. Bye.